Okay, so our homework today for 7.3 is we're talking about equilateral triangles, rectangles, and hexagons, but I'm looking at that and it doesn't make any sense, so I guess I better read the instructions, which say determine the angles of rotational symmetry, which we talked about in yesterday's warm-up, and the number of lines of reflective symmetry for each of the polygons below. So let's make sure we understand these bolded words. Angles of rotational symmetry mean the angles at which I can turn this triangle or rectangle and have it land exactly on top of each other. And lines of reflective symmetry are places where I can fold it and have the sides land on top of each other, and so on. So I think you can handle that. It shouldn't be too bad. But let's go down to 4, 5, and 6, which ask us to solve the right triangles. We're going to do number 6 together. Number 6 says that we're going to solve this triangle. So the first thing I'm going to do is find this missing side. And so we're going to have x squared plus 8 squared equals 10 squared, which gives me x squared plus 64 equals 100. So x squared equals 36. So x is 6. Once I have my missing sides, now I have to find my missing angles, which is why I chose this one, because when we took the test on this whatever that was, my brain is a little bit unclear about when that test was. But when we did take that test, we had the hardest time finding the missing angles. So now that we have that, we're going to find our missing angles by using inverse operations. So we're going to have the sine of, we'll call this one A. The sine of angle A equals 8 over 10, or 4/5. And so A is equal to the sine inverse of 4/5, which is approximately equal to 53.13 degrees. And so once I have that, I'm going to subtract that number from 90. So 90 minus 53.13 leaves me this angle is going to be 36.87 degrees. And so those are my two answers. That triangle is solved. So that's what you're going to do. Go ahead and finish up this warm-up. Pause your screen, and I will get the answers to you for it in just a moment. Okay, so and clean up number 6 a little bit, so the answers are the same. You have all the lines of symmetry in the equilateral triangle, 3 angles of rotation, 120, etc. This is not a regular polygon, so the only rotational symmetry it has is 180 and 360, 2 lines of symmetry. The regular hexagon, I'll talk about those lines of symmetry in a minute, but we've got 60, 120, 180, 240, 300, and 360. Now there are 6 lines of symmetry here, so I'm just going to trace them real fast. That's 1, 2, 3, 4, 5, 6. Just be careful. They go from midpoint to midpoint and vertex to opposite vertex. And that's what we're dealing with on the top ones. This one, number 4, I used, since it was a 30, 60, 90 triangle, I used my knowledge to figure that one out. So I got 1 half of that is 1/2, and the short side times the square root of 2 is square root of 2 over, actually that should be the square root of 3. See what happens when you're not being clear? Square root of 3 over 2. And then here we have the solving triangle, 72 degrees right here. This tangent one is the operation I did to find this missing side. To find this one, I did sine. I also double checked it with the Pythagorean theorem and was really close. So that's where those came from. And hopefully this problems didn't take you very long. Moving on. So today we're going to be talking about cyclic polygons. Cyclic means cycle, and a polygon, of course, is an object with 3 or more sides. And a cyclic polygon can be inscribed inside a circle. In Unit 5, we learned about finding the circumcenter, the orthocenter, the centroid, and the incenter. I don't know if we spent a lot of time on the orthocenter, if we even talked about it, but it's neither here nor there. We know that the circumcenter, which circumscribes the triangle, or means goes around the triangle completely, can be found by constructing all of the perpendicular bisectors of each side of the triangle. So that's what's in these pictures. I've already constructed the perpendicular bisectors for you. Of course, again, you don't have access to compasses, so it makes it hard to finish the construction. But all that means is I want you to draw circles. So what we're going to do is place our compass point on the big black dot that I've hand drawn, which is the circumcenter. Turn our compass so that we can line up and make sure that we are actually equidistant. And draw a circle. You'll notice that we have inscribed this triangle. It's cyclic because we can put a circle around it. And that's all I'm looking for here, is for you to continue to do that with the rest of them. So without a compass, it's practically impossible to do this accurately. You can wait till I get back to draw these circles, but the idea is still here. And then we're going to get into what it means, what's important about that point. So I want you to think about these 3 different triangles that we're dealing with and what happened that makes them different. And we'll read some words here. Since each vertex lies on of an inside triangle lies on the circle, each angle of the triangle is an inscribed angle. So we're going to be talking about the results with the inscribed angles. We know that the sum of the measures of the interior angles is 180 degrees. Excuse me. And the sum of the 3 intercepted arcs is 360. So what am I talking about? So intercepted arc, that's one of them. Intercepted arc, that's 2. Intercepted arc, that's the third one, and it's a circle, so it adds up to 360. So that's all that's talking about. Okay. So it just wants you to explain that, picking a circle above to talk about why that statement is true. So just think about it for a minute. I just finished explaining it, so if you need to back up the video and re-listen to it before you move on, write down what your answer is to that blank. Okay, so to finish this off, we're looking at what's happening with that inscribed angle and the angle, the central angle. So we know that the degree measure of an arc is by definition the same as the measure of the central angle that's formed by the radii that contain the endpoints of that arc. Let's make sure we understand what that just said. So given a circle and an arc on the circle, the measure of this arc is the same as the measure of the angle. That's all that's saying. The central angle being from the center to the edges. What we are trying to figure out is how this angle here, the central angle or the arc, because they're the same, relates to the inscribed angle over here. Notice this angle is intercepting the same arc. We're trying to figure out what their relationship is. Now this is very poorly drawn, and I'm not sure that, well, the blue one is definitely an inscribed angle. I don't know if the red one is a central angle, so we're not going to use this one. But the next, so that's the question. Now you're not ready to answer it here yet. We'll get to that. But right now, we're going to use a protractor, and again, you're going to have to do your best here to find the measure of each arc represented on each circle diagram, then find the measure of the corresponding inscribed angle. And what patterns do you notice? So what I'm asking you to do is going back here to these pictures, draw the central angles in and measure the central angles with your protractor and figure out how that relates to the inscribed, this angle, that angle, that angle. So I'm just going to do one for you and we'll see what's happening. So we have a very large protractor. We don't need it to be that big. Go for that small. Looks like 105 for this angle. And this central angle is strange because it's going to be this one. So that's going to be more than 180. So that's why the reason I chose to do this one for you. because I have fancy compass that goes all the way to 360 if I just turn it on all the way. So we're going to line it up. And looking at that, looks like it's, where's the 0? Not lined up with the 0. Give me a second. So 0. And then looks like it's 210. So my other angle was 105. This was 105. And this is 210. How are those related? It looks like I'm doubling that to get this. And so your goal is to measure the angles and see if that's true. So that's the goal for today. See what you can do, and good luck.